Thank you for the kind introduction and the possibility to present my research. And I will do this as best as I can. So the topic is higher harmonic analysis in IMPS and IMVS. And let's just begin. So I have structured this presentation so that to maintain the balance between mathematical rigor and clarity of presented physical phenomena, and I will try to maintain this balance throughout all the presentation. Although, I will just go briefly about introduction because the principle of IMPS and IMVS was very thoroughly discussed during this conference. And then I will again briefly try to convince you that the linear approximation is completely incorrect in most systems with experimental example. And then a little bit of my own theoretical development of this higher harmonic analysis for this technique and experiments for two model systems. So let's do this. Short review. I will use the phasor notation here so that I am using complex exponentials instead of cosines. So I'm doing this approximation to neglect the right and only positive frequencies, and I encode the phase into the phasor so that this tilde is a phasor, right? And this is kind of straightforward. And in IMVS, it is the case that ideally I input a periodically oscillating cosine of light intensity, P, and I expect to have a cosine wave of photovoltage. I apologize for using U for photovoltage, but it is U is a photovoltage, not V in this case. And this relationship I have discussed can be captured by those simple equations, right? Exponential as the input and exponential on the output. And if this would be the case, I would have been able to develop the concept of a transfer function, like this Fourier transform of a photovoltage divided by the Fourier transform of a power density. However, in order to do this, my relationship between photovoltage and power density would have to be this case, would have to be linear. If it is not linear, I cannot define the concept of a transfer function because those definitions is not satisfied. And as Professor Rysz presented in his talk, if we have a very simple case like RC circuit, we would have the frequency-dependent real and imaginary part of the photovoltage, which can be calculated using these equations like in-phase term and quadrature term. And the result would be presented on the Nyquist or Argand plot, or in case of a body plot in this case, right? So in this case, we have a single characteristic frequency and everything is all right. But it is an idealized case of a RC circuit, and our samples are more complicated than RC circuits. And yes, and in principle, there can be more characteristic time constants, so the picture is blurred. It is kind of complicated, yet much. And basing on the shape of those functions, one can infer the details of the mechanisms of recombination in case of photovoltage, of transport in case of IMPS, photocurrents, and several other phenomena also. So, yes, this is true. Linear approximation is incorrect. And I would like to show you how badly incorrect it is. Because it is terribly bad. For example, let's take the photovoltage versus P dependence of a photodiode. And in this case, it is completely nonlinear. I mean, one could say that the initial region is a little bit linear for the very small power densities, but as all the function, it is completely nonlinear. It is like this curve with characteristic saturation at some power density. And a short remark that this is 0% and this is 100% like a power density. I have calculated percents to the power density according to the calibration procedure. So we have exact numbers of power density. And typically in the literature, if one encounters such a characteristic, he is advised to use so much small perturbation. So let's see how small perturbation needs to be in this toy model, how small it needs to be for the linear approximation to be quote unquote correct. Let's just do a try. Let's zoom out in this curve in some regime. And okay, I have zoom. It is still nonlinear. Then let's do another zoom. Okay, it looks optically like it would be linear. However, I would like to notice that let's do this pointer also, because this doesn't seems not to work. But let's see that an amplitude of the light I would need to use needs to produce 4 or 5 millivolts of amplitude. Okay, in principle it could be manageable, but I am asking the question whether my sample is stable enough to be possible to register such small voltages, such small photovoltages in the noise of any other processes. From my experimental experience, it is impossible because I have noises like in the same range, few millivolts. So it is a serious problem. Even if I go low with the power density input, it is still nonlinear, right? It is this P should be so small that it is almost impossibly indistinguishable from the noise. So it is terrible. It is completely bad. And there is another problem. The problem is that I can do this quote-unquote literature approach in different points on the characteristic. And when I do different points, I get different IMVS spectra, and I have different characteristic time constants. So which one should I choose? Well, this does not give me an like complete knowledge of the material when I use linear approximation. So I hope that this is enough convincing to propose another more advanced tool to treat and study physical origins of nonlinearities than just using this barbaric, this barbaric treatment. And the answer to this is precisely analysis of higher harmonics. And a disclaimer of scientific honesty that several of results I present in the next slides is a part of the article I am currently preparing, so it is not yet published. This is for honesty. And in fact, I am assuming that I can express my photovoltage versus light intensity dependence as a Taylor series of this kind. So photovoltage is a Taylor series of a power density, and for dimensional convenience I introduced the constant P limit so that all the coefficients of this Taylor series have the unit of current. This constant is not necessarily, but it is also easy to see that if my P is greater than P limit, the Taylor series most presumably becomes divergent. So I want to P to be less than some p-limit, and considering experimental results, I see that the p-limit is not reachable in the power densities provided by the device, or it can be given infinity. So we are safe about this about the convergence of the series. I hope. This is my hope. I mean, this is assumption, but you need to start from somewhere. So if I have such a Taylor series expansion for the photovoltage, and I know that the input, I mean power density of light, is given by this simple exponential, I can plug it in, and give another series for photovoltage where this object and this photovoltage is expressed as a series of exponentials with I and omega t. So n equals 1 is the first harmonic, n equals 2 is the second harmonic, and so on. And this object is a nth harmonic of the photovoltage, right? And again, I pose a question whether this series converges, and physically yes, because this is experimentally proven that, for example, for 10th harmonic, the signal is just noise. And mathematically, it happens only if p is less than p-limit, and this is all right then. In practice, of course, we do not put here infinity, but for example 6 or 7 harmonics, and it is the case, right? So this is the series of higher harmonics. All the photovoltage can be decomposed in such a way. How should I know that higher harmonics are present into my output signal? Well, if I have a pure sine, it looks like this. And sometimes, if the harmonics are reasonably high, this could be looking like these two pictures on the right? So it can be captured by the naked eye, but sometimes it's not so easy to capture by the naked eye, though those signs are slightly curved. But a naked eye is not a good tool for this, but just a brief observation of those functions can give you a tool that they might be present. All right, I need to be careful. So if I get this knowledge, I can calculate spectra of higher harmonics and the real and imaginary part, because all these objects, U1 tilde, U2 tilde, are phasors. They have both real and imaginary part, and all those real and imaginary parts are frequency dependent, right? So you can go ahead and per analogy calculate real and imaginary part of the these integrals, right? This in-phase component and quadrature component, and do this for not only the first harmonic, but for the nth. So this is n equals 1, this is first, and n equals 2, this sine of 2 omega t, cosine 2 omega t, and so on. And therefore you obtain real and imaginary parts of first, second, third, and all the other harmonics. So this is the very complex but manageable. It is manageable, and I will later solve the transport equation that was presented by Professor Rysz for a very the simplest case, which all those higher harmonics can be analytically obtained actually. But before I do this, one simple additional remark, observation, because for now I was using complex exponentials, so I have neglected negative frequencies, but let's do this, what happens when I do not neglect this, right? So I have, for simplicity, I assume quadratic dependence of photovoltage. Just for simplicity, all the other terms can be there, but I now apply cosine wave, so I have positive exponential and its complex conjugate, which is a negative exponential, and I plug it into the Taylor series, and I get linear and nonlinear response, and what those responses are. So the linear response gives a linear, from 1 Hz frequency input, I get 1 frequency output, 1 Hz frequency output, nothing fancy. However, in case of nonlinear response, I have the second harmonic, right? But I also have another contribution for the first harmonic. This is just a single omega. So I think that I measure the first harmonic if I do not have this nonlinear assumption in the model. I think that I measure the first harmonic, but I measure the first harmonic plus something else, plus exactly this term, plus even other terms from the cubic term, quartic term, and so on. So when the sample is nonlinear and I measure only the first harmonic, I measure all the harmonics, all the coefficients of higher harmonics give a contribution even to the first. The sample already knows that it is nonlinear by those, only the first harmonic, it already knows, possesses this information of the nonlinearity. This is like a curious, information. And now, yes, this is precisely what I have told so far. And let's see how those higher harmonics can be analytically derived for a very simple case, and what should we expect from them? How should they look like? This is the slightly modified version of the damped oscillator equation presented by Professor Rysz. However, I have included another term, this blue, this is overall change in the electron density, because n is electron density. This is diffusion, because we have diffusion coefficient, we have a Laplacian, and here is an external field. Here is the migration, right? We have phi as electrostatic potential, and the second derivative, like Laplacian of this, so it gives a drive, migrational component to the transport. And I have a recombination, and I have a generation. So the simple is kind of complete, and this is equation for electron density, not for hole density, because introduction of holes is not necessary to capture the experimental result. That's the message, that no holes are needed. Okay, so the simplistic case, this equation could be solved without this assumption I will tell, but for the simplicity of mathematics, I decided to do this simplification. And the simplification is that those two Laplacians are constants. Well, are those approximations reasonable, right? Because in case of IMVS, it is quite reasonable, because current is defined as this spatial derivative. Well, I apologize for using standard symbols like standard Ds. They should be curly derivatives, like partial derivatives, but I could not export this symbol from the. Never mind. These are partial derivatives. Backing to the main concept is that the current is defined like this spatial derivative, and in IMVS it is equal to 0, because we have an open circuit potential. The circuit is and the current is 0. Therefore, the second derivative must also be 0. So derivative of F0 is again a 0. So this approximation is reasonable for IMVS, and for IMPS it is it is a strong approximation, although it is still physical, and it is mathematically equivalent to putting a very specific ratio of charges on the right and left terminal. Not going into details about it, but it is okay. The approximation of this one constant is approximation that the electric field inside the space charge region is a constant electric field. Okay. Okay, so this is the approximation, and the result is a picture of kinetic equations that was being developed 30 years ago by Ellen Peter and other colleagues of his, and this is the result, and this result is only time dependent. This is easy. This is single variable ordinary differential equation. This is easy. It is very easy to solve. You do not need to apply some higher level mathematics to do so. And typically in the literature, as Professor Rösch have shown, typically in the literature, this shape, this kind of generation current equation is used as an input. And if it is true, then we get a solution for electron density, time-dependent electron density, like this, again simple exponential. But it is not true. This is my claim that it is not true. And because this is a linear approximation embedded here, because from the single harmonic I get the single harmonic. So this is not true. This is not true. Instead, I propose a new expression for this. That can be manufactured similarly to the thing that I have shown on previous slides, and the result is that the generation current has its own higher harmonics embedded in this symbol, right? This is IN. This is a kind of nth harmonic generation current. Okay, so this is the input to this equation as a generation current, which results in the solution for electron density having, again, its higher harmonics. And this coefficient can be very easily captured. In this case, it is very easy. In other cases, it is slightly more difficult. But in this very simplified case, this is a very simple function, right? Simple fraction. And now the definition of a photovoltage. The definition of a photovoltage is like it is a charge over some object. In the very simple case, it could be regarded as space charge capacitance, and I will do this for didactic purposes, although in general, it is not a capacitance, it is somewhat relating the photovoltage with charge. Well, in the simplest case, it is a scalar, but it's more complicated and advanced treatment. This would be a function. This would be a more mathematically complicated object. But nevertheless, in the simplest possible case, this is photovoltage. This is the electron density I have calculated here. So I plug it in, and I compare this with the definition of the higher harmonics of the photovoltage, and this is the result, right? This is the most simple solution for higher harmonics with this very, very simple, very, very crude model. I obtained this result. How does it look like? Well, it looks like this. I mean, this is real and imaginary parts, and in this case, the real part looks like Arcus-Tangens function, for example, and I used IN coefficients to be decaying in some fashion. However, experimentally, by measuring your spectra, you can resolve those coefficients by, these amplitudes are proportional to this. So, using experiments, one could get the decaying. One could get insight into the shape of those nonlinear coefficients for generation current. Moreover, one can see that the characteristic frequency of the first harmonic, for example, 300, is decaying for the next harmonics like 1 over m. This is the thing I should expect, that higher harmonics should have smaller characteristic frequency and also smaller amplitudes in some way. So, and again, important remark is that it is a very simple solution. nonlinearities can be captured in several other ways. I have explored also p-dependence of recombination constant, p-dependence of a space charge region capacitance, and several other things can be also shown, but for didactic purposes only I show only this case, but because it is quite accurate if you see the experiments now. So experiments for IMVS for the silicon photodiode and IMPS for titanium dioxide. So this is like toy models I have used for my studies. So this is results for silicon photodiode, and the curious thing is I have used literaturally preferred way with the smallest AC, with a very small AC amplitude of the input to neglect the higher harmonics, but it does not work because even if in this smaller, small input, I have the second harmonic and it is quite big. You cannot avoid this. And if you compare these results with the previously shown picture, indeed, recombination constant is decaying. Indeed, amplitudes are decaying. Indeed, those curves, amplitudes are also decaying. So this is something in it. Again, the same thing with still the smaller, the smaller amplitude in different place of the characteristic, and I have also higher harmonics, but they are different. These are okay. This is a small, and now will be not small amplitude, but full amplitude, full spectrum, like from the beginning to the end, full power of the LEDs, and the result is the following: we have all spectrum of higher harmonics, and the real part again behaves similarly to the predicted as a model. Imaginary part is a more complicated slightly because higher harmonics reveal processes that are not seen by only the first one. By looking at the first one, okay, I have a single Lorentzian, I have a single time constant, but in the second harmonic I have the first and some other shoulder peak. On the third I have, the peak and something else, and again, these characteristic frequencies are decaying with the harmonic number. Okay. And by comparison of this, well, shall I put? Okay, the general message is that this very simplistic model for higher harmonics is giving a rough picture of what should happen, but it does not reproduce experiments to the 100% because of those another processes that need to be added into the transport equation at the first place. Or it could be power density dependence, constant of recombination, or other things. Not going into details here. This is just an advertisement of what can I get from the higher harmonics, and it is clearly seen that the information is richer. Yes, those are those shoulder peaks I have mentioned. Information is undoubtedly richer than from the first one, and this is a tool for getting this information. And if I do the deconvolution to Lorentzians, this, like this, and I have plotted the characteristic frequency with the harmonic number, it is like 1 over NDK. So this model is kind of quite good. Well, this is a silicon photodiode, IMVS. So now let's do IMPS for titanium dioxide. Photodiode is not a good toy model for IMPS because it is quite linear. This device is made such that it should be linear, but titanium dioxide is a better toy model because it is nonlinear, and here we see the proof of this nonlinearity. This photocurrent intensity dependence is not linear. Well, this is the shape. And initially, I thought that the pure titanium dioxide would be a good model. We will verify this. And but I have also done some modification, some surface modification and it also gives a nonlinear effect, but characteristic is a little bit different. What is so important about this is that a pure titanium dioxide does not exhibit higher harmonics, at least in a short circuit conditions. Okay. I have some high frequency constant involving in transport, some low frequency characteristic frequency involving with recombination, with double layer charging and other phenomena, but higher harmonics are absent, so maybe there is something wrong. However, when I do after modification, I have this picture. Oh, this is kind of interesting because after purely surface modification, this is particularly this is a particular kind of surface hydrogenation, but details are not important. This is just an advertisement of the possibilities of higher harmonics. So let's take a closer look, not on the first one because the first one is let's take a closer look on what happens in this regime of higher harmonics. Let's take a look. So they have this shape, right? This shape is quite more complicated because the system is more complicated, and for example, from 2 characteristic frequencies, I have 3, again 2, and they decay somehow. This is a very complex system actually, and the answer is that in this system there are strong dependencies of a I'm a little bit tired now, so the thinking does not go so easily, but the general conclusion is that the physical reason is the power density dependence of different constants in the transport equation. I do not want to go deeply in discussing the results, but this is the power of higher harmonics, and it can be explored for any materials because this space is very, very powerful to explain the physics of and chemistry also of samples. So this is the advertisement for you to maybe also use this technique, this approach, and develop this further, this higher harmonics analysis. And the conclusion is that even with the smallest possible light perturbation, higher harmonics also appear and also add to the spectra, and information that could be withdrawn from higher harmonics is richer than solely for the first harmonic, and mathematically this could be obtained, the shape of those harmonics can be obtained by solving Nernst-Plant equation with different, assumption. I have this kind of recombination, this kinetics, that kinetics, this dependence. This is a very complicated picture. I do not want to make complicated more, but this is a very rich space to explore. So thank you for your attention. Thanks for my supervisor, Katarzyna Siuzdak and Robert Bogdanowicz from Gdansk Tech and from IMPS. And thanks for Instytut Fotonowy for giving me the device and software, and for funding for my Diamond grant and other sources that were used. So that's all my message for today, and thank you for your attention, and that's all. I hope I am in time. Sure.
I would like to ask you. Okay, but how, for this IMPS measurement, how did you solve the problem of zero voltage across the sample? Was it 3 electrode or 2 electrodes measurement?
This is very important. This is 2 electrode. This is 2 electrode because actually this is the only sample that allowed creation of higher harmonics in 2 electrode configuration. This is a miracle, I suppose, because in most cases I need to use 3 electrode system, but this system was exceptional because it was 2 electrode measurement. So this is, short circuit. Indeed, this is short circuit.
Yeah, it's very impressive what you've done. And any more questions? Okay, let's thank our speaker again.